Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we're going to cover something that is essential to understanding organic chemistry reactions, and that is arrow pushing. This video will focus on understanding full-headed arrows. A full-headed arrow is used in organic chemistry to represent the movement of two electrons. An arrow is drawn from a region that contains two electrons, that is, a bond or a lone pair, to an area that will be receiving the electrons. The base of the arrow is where the electrons start, and the head of the arrow is where the electrons are being moved to. Arrows are used to show how reactions work, in other words, reaction mechanisms, or to help understand resonance. A single full-headed arrow can be used to represent one of three things. Turning a lone pair into a bond, we call that making a bond. Turning a bond into a lone pair, we call that breaking a bond. Or turning a bond into another bond, that is both breaking and making a bond. In our first example, a lone pair on a chloride anion attacks the electron-deficient carbocation. The electrons from the lone pair are used to create a new bond, in red, between the chlorine and carbon. In our second example, the electrons in the bond between the carbon and chlorine are transferred to the chlorine. This breaks the bond between the carbon and the chlorine receives the two electrons, and the carbon is now electron deficient. In our third example, the electrons in the pi bond on the benzene ring attack the electron-deficient carbocation, breaking the pi bond and leaving behind a new carbocation at one of the two carbons from the ring. The electrons from the pi bond are used to form a new sigma bond between the other carbon from the ring and the carbon from the original carbocation. Before we continue with specific examples of arrow pushing that you'll encounter in organic chemistry, I want to point out that all of these examples on the remaining slides are already completely explained by what we covered on the previous slide. That is, in all of these examples, we will simply be making a bond, breaking a bond, or both. Let's talk about arrows drawn from lone pairs to an atom or to a bond. When an arrow is drawn from a lone pair to an atom, the electrons from the lone pair are used to form a new bond between the atom that originally had the lone pair and the atom that the arrowhead was drawn to. When an arrow is drawn from a lone pair to a bond, a pi bond is formed. On the previous slide, you already saw this first example and the description of the first example. For these remaining examples, see if you can predict the product by drawing your own, and also see if you can come up with an accurate description that describes the arrow pushing. So pause the video, give it a try, and when you're ready, unpause it and see what we have. In our second example, a lone pair on the oxygen from the water molecule attacks the electron-deficient carbocation. The electrons from the lone pair are used to create a new bond, in red, between the oxygen and carbon. Note that the two hydrogens that were originally bonded to the oxygen are still bonded to the oxygen. We only drew one arrow, from the lone pair to the carbon. That means we should not touch anything else in either molecule. In our third example, a lone pair on the chlorine atom attacks the electron-deficient aluminum. The electrons from the lone pair are used to create a new bond between the chlorine and aluminum. Once again, that is the only arrow that we drew, so all of the other remaining bonds remain as they were before. In our final example, a lone pair on the oxygen is shown coming down to the bond between the oxygen and carbon, creating a double bond. This is not a reaction, but it shows the free flow of electrons among adjacent p orbitals in resonance. In our next category, we'll be reviewing arrows from sigma or pi bonds to an adjacent atom. When an arrow is drawn from a sigma bond to an adjacent atom, that is, one of the atoms that was already connected to that sigma bond, the bond is cleaved, resulting in the separation of the groups that were connected via the bond. The atom to where the arrowhead was pointing receives the two electrons from the sigma bond. This will be drawn as a lone pair on that atom. and the other atom loses 2 electrons. When an arrow is drawn from a pi bond to an adjacent atom, the atom to where the arrowhead was pointing receives the 2 electrons from the pi bond, once again drawn as a lone pair, and the other atom loses 2 electrons. The 2 atoms that were joined via the pi bond are still connected via a sigma bond, however. Once again, our first example was covered a couple slides ago. So for the next 2, go ahead and pause the video, and then unpause it when you're ready to see the answer. In this second example, the electrons in the pi bond between the carbon and oxygen are shown going up to the oxygen, breaking the pi bond, but leaving the sigma bond intact. This is not a reaction. In fact, it is just the reverse of what we saw on the previous slide, and once again, it shows the free flow of electrons among adjacent p orbitals in resonance. Our final example may have been a little tricky for you, as the reaction depicts 2 different arrows, with one of the arrows, the red one, showing something that we haven't explicitly talked about, drawing an arrow from a bond to a non-adjacent atom. However, using the original principles of electron pushing that we covered in the second slide, you may have been able to piece this one together. But for now, let's just focus on the blue arrow, and we'll cover what happens with the red arrow soon. With the blue arrow, the electrons in the pi bond between the carbon and oxygen are transferred to the oxygen, breaking the pi bond, but leaving the sigma bond intact. You can see that represented in the first molecule to the right of the arrow. For our next subcategory, let's discuss arrows from sigma bonds to non-adjacent atoms. When an arrow is drawn from a sigma bond to a non-adjacent atom, that is, an atom from another molecule, or an atom from the same molecule that is not already connected to that sigma bond, the bond is cleaved, resulting in the separation of the groups that were connected via the bond. The atom to where the arrowhead was pointing forms a new sigma bond, with one of the atoms participating in the original sigma bond. Oftentimes, this is the more electronegative atom. The atom that didn't form a new bond loses 2 electrons. So once again, pause the video and draw the products to these 4 reactions. In addition, try to verbalize what each of these arrows means. In our first example, the electrons in the bond between 2 carbon atoms are transferred to a carbocation, breaking the bond and leaving behind a new carbocation. The electrons are used to form a new bond between the methyl group's carbon and the original carbocation. The next example is a little bit trickier to understand. What happens is the electrons in the bond between the 2 carbon atoms are transferred to the carbocation, just like in the previous example. This breaks the bond, and when it does so, it opens up the 5-membered ring. It also leaves behind a new carbocation. The electrons from the bond that we broke are used to form a new bond, creating an expanded 6-membered ring. I know that may be a little bit difficult to process at this point in your study of organic chemistry, so I've gone ahead and numbered the carbons on the molecule on the left and the molecule on the right, so that it's easier to figure out which atom connects to which atom and which bond is broken. You can see that in the original molecule, carbon 3 was bonded to carbon 7. That arrow shows the breaking of the bond between 3 and 7. Carbon 3 does not get a bond back in return, and now it is a carbocation, as you can see on the right. In addition, carbon 7 is now bonded to carbon number 2. That's why we have a 6-membered ring. Hopefully that clears things up for you. Our third example looks very similar to our first example, except we have a hydrogen instead of a methyl group. The electrons in the bond between a carbon and a hydrogen are transferred to a carbocation, breaking the bond and leaving behind a new carbocation. The electrons from the bond that we broke are used to form a new bond between the hydrogen and the original carbocation. These first 3 examples are all examples of what we call carbocation rearrangements. In the first one, we did a 1,2 methyl shift. In the second, we did a ring expansion. And in the third, we did a 1,2 hydride shift. For more information on carbocation rearrangements, check out the carbocations video. In our last example on this page, we're going to talk about that red arrow that we alluded to on the previous slide. The electrons in the bond between the carbon and magnesium attack the electron-deficient carbonyl carbon. That's the carbon double bond to the oxygen. Since we are attacking from a bond, that bond is going to break, separating the carbon from the magnesium. That's going to create an MgBr cation, as the carbon is more electronegative than magnesium and holds on to those electrons more closely. Those electrons are used to form a new bond between the ethyl group's carbon and the carbonyl carbon. You can see that new bond in red. Next, let's talk about arrows from pi bonds to non-adjacent atoms. When an arrow is drawn from a pi bond to a non-adjacent atom, the pi bond is cleaved while the sigma bond remains intact. The atom to where the arrowhead was pointing forms a new sigma bond with the more electronegative atom of the two atoms participating in the original pi bond, or, if there's no difference in electronegativity, the less substituted atom. The atom that didn't form a new bond loses 2 electrons. The first example shown here is something that we covered early on in one of the original slides. For the remaining 3 examples, pause the video and see if you can draw the products as well as come up with your own description of what's happening. In our second example, if we're focusing on the red arrow, the electrons in the pi bond attack an acidic hydrogen, breaking the pi bond and leaving behind a carbocation at the more substituted carbon. The electrons from the pi bond are used to form a new sigma bond between the other carbon and the hydrogen, as shown on the products on the right. The blue arrow simply shows the chlorine being cleaved from the hydrogen and gaining the electrons. In our third example, looking at the red arrow, the electrons in the pi bond attack an electron-deficient boron, breaking the pi bond and causing the more substituted carbon to temporarily become partially positive. The electrons from that pi bond are used to form a new bond between the other carbon and the boron, as shown in red on the right. The blue arrow actually represents something we just covered on the previous slide, an arrow from a sigma bond to a non-adjacent atom. Here, since the hydrogen is more electronegative than the boron, the bond between the hydrogen and the boron attacks the carbon that just became partially positive as a result of the pi bond attacking the boron. That's how we get a new bond between that more substituted carbon and the hydrogen, as shown in blue on the right. In our final example, once again, we'll focus on the pi bond attacking the non-adjacent atom. That's the red arrow. The electrons in the pi bond attack an acidic hydrogen, breaking the pi bond and causing the carbonyl carbon to temporarily become partially positive. The electrons from that pi bond are used to form a new bond between the oxygen, which is the more electronegative atom of the carbon and the oxygen, and the hydrogen. You can see that new oxygen-hydrogen bond on one of the products on the right in red. Last, we're going to focus on arrows from sigma or pi bonds to adjacent bonds. When an arrow is drawn from a sigma bond to an adjacent bond, the sigma bond where the arrow began is cleaved, resulting in the separation of the groups that were connected via the bond. The bond to where the arrowhead was pointing receives the 2 electrons from the broken sigma bond. That is, a single bond becomes a double bond, or a double bond becomes a triple bond. When an arrow is drawn from a pi bond to an adjacent bond, the pi bond is cleaved, while the sigma bond remains intact, of course. The bond to where the arrowhead was pointing receives the 2 electrons from the broken pi bond. Go ahead and pause the video and work on these 2 examples. In the last slide, we covered what the red arrow did. In this slide, we'll discuss the blue and green arrows. For the blue arrow, the electrons in the sigma bond between the oxygen and hydrogen are transferred to the space between the carbon and oxygen, forming a new carbon-oxygen pi bond and breaking the oxygen-hydrogen sigma bond. For the green arrow, the electrons in the sigma bond between 2 carbons are transferred to the space between one of the carbons and an adjacent carbon, forming a new carbon-carbon pi bond and breaking the original carbon-carbon sigma bond. In our final example, The electrons in the pi bonds on the benzene ring are shown moving to adjacent bonds, breaking the pi bonds and forming new ones. This is not a reaction, but it shows the free flow of electrons among adjacent p orbitals in resonance. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.